Welcome back to the course in nuclear medicine physics. Today, we'll be looking at the interaction of charged particles with matter. Now, this is essential for nuclear medicine, where all radiation treatment is essentially the interaction of charged particles with biological matter. There's two really important quantities that we'll define in this lecture, and that's stopping power and linear energy transfer. Both these quantities have to do with how charged particles lose their own energy when traveling through matter and transfer it to matter. Please remember to like and subscribe if you enjoy this series, and enjoy the video.
Hey, good morning everyone again to another lecture of this physics in nuclear medicine. Today we're going to talk about interactions of radiations with matter, but before I dig into it, let's do a quick wrap up. So we started talking about how an atom looks, then we talked about radionuclide decay, and we know that there are particles coming out of there. Then our man showed how we can combine these radioisotopes and talked about some different molecules to target different processes in the body. But keep in mind that our goal is to at some point be able to create images of this, and at some point understand why is that we can use these particles to treat disease. And that's where these interactions of radiation with matter become so handy, because if we understand these, then we are gonna know, or we're gonna have an idea of how is that we can build detectors for it. And this is how we're also gonna know how is that we're gonna use these particles to destroy the DNA in cells to, say, for example, try to cure cancer. So let's get started with this then. Okay, so when we talk about the interactions of radiation with matter, we're interested in seeing what's the energy lost by the particles that are traveling in that medium. We're interested in knowing if there's some radiation change. So we're going to look in detail, but for example, a positron will annihilate with an electron, and it's not going to be a positron and an electron anymore. This is going to change the type of radiation. Are there any changes in the material? So for example, is it going to be damaging that material? Are we going to cause some of those cells to die? So let's take a look. So we're going to start talking about interactions of charged particles. We're here mainly concerned with particles with energies between the 10 keV and 10 MeV. So let's look. So when we have charged particles interaction with matter, and charged particles, I mean, of course, for example, alpha particles or beta particles. We have one of these particles traveling inside some medium, they're going to be losing energy as they travel. Why do they lose that energy? Well, this is caused because they're going to be colliding with other atoms and molecules in the medium. And then we can think that maybe additional high energy electrons are going to be released from those atoms. So you have your initial particle, maybe there's going to be an electron from an atom that's going to be knocked out, and maybe that electron is going to be able to cause other electrons to freely move in the medium. Gammas and X-ray will also cause some electrons from atoms to be ejected. And then if that happens, then we'll know that we might end up having some internal conversion and Auger electrons as well. And these are also charged particles that are going to be traveling in the medium. So one charged particle can then cause other charged particles to travel in the medium. Electrons, or beta minus and beta plus particles, experience the same forces of interaction, except that there's a difference in the direction of the force. If it's a negatively charged or a positively charged particle, we've talked in the past that electrons and beta plus are basically the same particle in the sense that they have the same mass. So the beta particles come from the nucleus, and then, well, of course, positrons and electrons, just the difference is the charge. So in general, if you see me referring to a beta particle from the rest of the talk, just keep in mind that what I will say for a beta particle will also apply for an electron, will also apply for a positron, unless I just explicitly say that it applies to only one. So these charged particles, as I said before, they lose energy and slow down as they travel through matter. So let's imagine one charged particle that I'm showing in yellow that is moving closer to one of the atoms in that medium. So because this particle has some charge and this atom has some charges, it has some electrons in the orbit, it has some positive charges in the nucleus, there will be some Coulomb interactions, whether with the nucleus or with the electrons, or whether this particle is positive or negative. That force is going to be either attracting or repelling. And then there's going to be situations in which that Coulomb force is strong enough that can cause two things. Either it can move an electron to the outer shell of the atom, like as we see here, or it can remove an electron from the atom, like we see here. So in the first case, we call that an excitation. So this particle traveling in that medium excited this atom, or this particle traveling in that medium ionized this atom, because now there's a charge that we lost. So this atom is now positively charged. One of those negative charges left the atom. So those are the two big effects that we see when charged particles interact with matter: excitation and ionization. So let's think a little bit about this. So is this true or false? The energy lost by a charged particle in an ionization event is going to be equal to the binding energy of the electron to the atomic shell where it was removed from. So true or false? Ten more seconds. Okay, I'm gonna leave 10 more seconds because it's interesting. Okay, let's stop the poll. I'm gonna share the results. So we have a 50-50. That's interesting. Let's think about it. Okay, so I'm saying that this particle is losing energy because it's transferring some energy to that electron. So it is true that to be able to knock out that electron from that shell, we need to be able to at least have a binding energy. So if this particle transfers just the binding energy, then, well, the electron will be free. However, this particle can transfer more than just the binding energy, because this electron can have a lot of kinetic energy. So because of that, I think the correct answer here is false. It doesn't necessarily just have to be, it doesn't necessarily just loses the binding energy. It can transfer way more, and then this electron can have a lot of energy. So in that case, it will lose the binding energy plus the kinetic energy of that electron. Are we clear with that? I know it was tricky, and that's why we got the 50-50, but that's why I had this question. I wanted you guys to think, make sure you understand this electron can have a lot of kinetic energy. This particle can lose much more than just the binding energy. Okay, so then we can think about these effects as collisional losses, which is basically what I called ionization before, typically ionization. So they don't really, I mean, although typically we refer to them as collisional, we don't mean that the two particles actually touch each other and collide. Well, it's not really a collision. It's more that interaction of that electrostatic, electromagnetic force. They don't have to be in contact, but that's what's really causing the interaction. So that initial charged particle can transfer enough kinetic energy to the secondary electron, like this one, okay, initial particle, we knocked out an electron. This electron can have a lot of kinetic energy, such that then this electron can go and do something similar to what just happened here in other atoms. And when we have those kind of scenarios, we call this electron an electron that has enough energy to cause some other ionizations. We refer to those as a delta ray. So a delta ray are electrons with enough energy. So what do you think is going to happen from having that ionization what happens when the ionization occurs from an inner shell electron?
Carlos, the poll is true or false. Can you do a multiple choice?
Yeah, thanks. Okay, so what happens? We have an ionization event. That ionization occurs from an inner shell electron. Then what's going to happen after we have an ionization event? It's going to be, we're going to have characteristic X-rays. Are we going to have OJ electrons? Are we going to have both? Or, well, ionizations will only really occur from outer shell electrons. Okay, I'm gonna solve the poll. This seems like everyone, most of the people agree is gonna be C. So yes, if we have now an empty shell, an outer shell electron can fill that shell, we're gonna have a characteristic X-ray. Or that electron filling that shell can then transfer energy to release another electron from the atom. We can have an OJ electron. So the answer is A and B. And D, well, I'm saying ionization only occurs from outer shell. Okay, so just to be explicit, the correct answer, yes, it was C, A and B. Okay, so, but in reality, yes, this ionization will typically mostly occur on outer shell electrons. It doesn't mean that there's not also a probability that it also happens for inner shell electrons, but there's a much higher chance that it happens for electrons in the outer shells. So far, everything that I've talked so far is looking at that charged particle interacting with the atom as a whole. So it's outside of the atom kind of thing, and we're able to release particles. But what happens now if that charged particle is able to penetrate the electron cloud? So we're gonna think this, it came down to the electron cloud, it has some charge. That interaction is not gonna happen mostly with the nucleus. So for example, if you have a charged particle like an alpha particle or a proton, then it can be, we can initiate something as what we discussed in the lecture of production of radioisotopes. These alpha particles or protons can actually end up making it into the nucleus, and we have a nuclear reaction. However, there's another type of interaction that is actually more likely to happen than just starting a nuclear reaction. And that is what we call radiative losses. So when you have this particle, in this case, I'm showing a Bethe minus particle, it's coming, it penetrates the electron cloud, there's a positive charge. This particle is gonna have an acceleration, it's gonna be bent. And when that particle is deflected because of that electric field, then this causes the initial particle to lose some energy. And that energy is released as an electromagnetic radiation. So there's photons coming out because of that bending. Now, those photons receive the name of Bremsstrahlung photons. And Bremsstrahlung, well, it has this name because Bremsstrahlung is basically a word in German that means breaking radiation, kind of stopping radiation, because this particle is accelerated, is being stopped, it releases those photons. So let's think about it. So now, what would be the energy of that Bremsstrahlung photon? So again, you have particles that are being accelerated because of the electric field. There's electromagnetic radiation coming out. What is that energy of that electromagnetic radiation? Okay, 5 more seconds. And okay, so I'll share the results with you. Most people went with D. Some people went with the other options. Turns out, yeah, well, the correct answer, I'm not exactly sure. I wasn't sure if all of the above is really the true representation, but yes, those emitted Bremsstrahlung photons can have all those energies. Basically, there's no photon being emitted, or it can take all the energy of the initial particle, or it can take 1/3. Let's look at that. I have that in the next slide. So if you look at this, these are actually some simulations that I ran in the past, in which I put some particles in water, and I just went to see how does that Bremsstrahlung spectrum look like, looking at what is the energy of those Bremsstrahlung emissions. So yeah, so there can be 0 when the initial particle is basically not deflected. The particle just goes, the interaction is very, very, very weak, basically nothing. So the particle doesn't lose energy. Or it can be the particle is basically completely stopped. So then the Bremsstrahlung photon takes all the energy of that initial particle, but then it can be a lot in between. And just keep in mind, this is a logarithmic scale here on the y-axis. But yeah, you can see different energies. Here are some electrons in water, electrons on different energies. And these are actually radioisotopes that have a beta minus decay. So I was looking at how those beta minus particles emit radiation when they're traveling in water. The dashed lines, yeah, it's not very clear here, but dashed and solid lines was just a different volume of water in which those particles were traveling. So yeah, so the message here is that Bremsstrahlung spectrum is a continuous spectrum, similar to what we talked back in the days when we saw the spectrum of beta decay. Okay, let's think this. I have another question here. So for which of the following particles, let's assume the initial energy is the same for all, and they're traveling in the same medium, would you expect a higher contribution of radiative effects? So you have all these cases, all these particles. In which case do you think you're going to have more Bremsstrahlung?
So the question is for Bremsstrahlung specifically.
Yeah, the question is from Bremsstrahlung.
Some of these can be tough questions because you're just seeing these for the first time, some of you. So just hang in there. Try to think, work through them.
Okay, so I'm gonna stop it. Well, most people answered C. There's also a lot of people answering A. Some people think it's the same. So let's look at this. Those are the slides that are coming. So keep this in mind. Some people answered electron or beta. Some people think it's more alpha. So we're gonna answer that question. So when you have radiative losses, okay, so let's think about this moving charge particle as having a mass m. And let's think that it has a charge Ze. So for example, if it's a beta particle, then it will just be E. If it's an alpha particle, then it will have 2 protons, so it will be 2E. That's what I mean with that. And let's think about the nucleus. The nucleus will have a mass Mn and a charge Ze. So if you have a charged particle with this charge and the nucleus with this charge, we can see that the force between the two, because of that electrostatic, that Coulomb interaction, will be a constant times charge 1 times charge 2. So that's why we have Ze times Ze. that gives ZZE squared. One is capital Z, the other one is lowercase z, and then divided by the distance. So if this is the force, then you can think about the Newton's law, force equals mass times acceleration. And the acceleration of that traveling particle is going to be that force divided by the mass. And we can basically assume that, especially for beta minus particles, but in general, that the mass of that particle, of that charged particle traveling in that medium is much, much smaller than the mass of the nucleus. So in principle, basically, the acceleration in the nucleus is just going to be much, much lower than the acceleration that that particle feels. So the nucleus is basically not going to move. And then, well, if you look at electromagnetism, there's this thing called the Larmor formula, and it's basically, what it tells us is when a charge is accelerated, that charge is going to emit some radiation. And that comes from the Larmor formula. You can then go and look in more detail for the derivation. But what this is basically is like the power being irradiated, or it depends on some constant, on the charge of that particle, on the acceleration of that particle, and the speed of light. Sorry, I was looking at the chat. So then we see, okay, the power being irradiated is basically proportional to the acceleration squared. So that's proportional to the square of the acceleration. So we have the acceleration here. We know that the power being radiated is proportional to this square. So again, so look at these equations, look at this acceleration, and let's answer this question again. So for which of the following particles, assuming the initial energy is the same, would you expect to have more Bremsstrahlung? Look at this equation, acceleration square. Look at this. Which particle is going to feel a higher acceleration is basically what I'm asking. Okay, I'm gonna give 10 seconds. Are you guys all done? Okay, let's stop this. Okay, let's look at the results. So now A and C became closer. So let's look. Okay, so let's look again at this formula. So what is heavier, an alpha particle or a beta particle? So basically, I don't know, a beta particle is composed, let's say, of 2 protons, 2 neutrons. We know that the mass of an electron is basically like 4 orders of magnitude less than a proton, so it's way smaller than the alpha particle. So this acceleration is going to be much higher for a beta particle than for an alpha particle. So if you have this acceleration that is basically orders of magnitude higher, then this radiation is going to be like the contribution of this radiation is going to be much bigger for the particle that has the least mass. So again, it's because of that. The correct answer for this is actually the electron or the beta particle. It's because the mass has a big influence. So you can think about, okay, what I was saying at the beginning, Bremsstrahlung is caused by having some acceleration kind of stopping, that's what it means in German, stopping radiation. You're trying, this interaction is stopping that particle. So what is easier to stop? A very, very big truck that's moving towards you, or a little fly that is moving towards you? So it's easier to stop the fly. It's harder to stop the big, big truck. So it's similar here. It's harder to stop that heavy alpha particle. It's easier to stop that electron. So if it's easier to stop, you're going to have more radiation.
So even though the alpha particle has higher Z or Z value, but still the mass difference is not comparable, right? To an electron. Because somebody might look at the Z or the Z at the top and they say, oh, alpha has higher value, right?
So let's see. And then, okay, because you can look at the charge, you can say, okay, the alpha particle has twice the charge. But twice the charge is not as big of a contribution as having basically 4 orders of magnitude difference in this denominator. And then 4 orders of magnitude difference in the denominator square is basically 8 orders of magnitude in that denominator. So that's kind of the main effect. Let me see. What is the determining? Okay, wait, let me read the questions. What is determining the frequency of the radiation? I think I'm gonna answer that question to you in a moment. Let's keep going, because I think I have answers for those couple of questions that are there. Yeah, so this is what I was just saying. Because this is proportional, then Bremsstrahlung is more important in 1, high Z materials. Again, we see this, the radiation is going to be proportional to that. So if you have this particle traveling in lead, you're going to have more Bremsstrahlung than the same particle traveling in a lighter material, like let's say in hydrogen, or in hydrogen gas, for example. And
sorry to interrupt. Just to be totally clear, can you say again what the small z and the large big Z, capital Z are?
Yes. So the big Z, I was referring to how many charges you have in the nucleus. And the small z was basically how many charges is this charged particle traveling in that medium. How many charged particles does you have? So I put that small z because if you have an alpha particle, that small z would be 2, but maybe you can have 3 protons traveling together, or only 1 proton. So it's kind of referring to the charge of the particle traveling in the medium. So that is small z. Big Z is how many protons do you have? It's basically the atomic number of that nucleus. And then this m is the particle of that, the mass of that particle. Are we clear? Any questions about this? Look, so again, Bremsstrahlung, if you have a higher Z material, higher capital Z, you're gonna have more protons here. That acceleration is gonna be higher. Then, of course, you're gonna have more emission because of it. And light particles, if this mass is lower, then this P is gonna be higher. So, I have a type of an equation there, but so we can have an approximation, and this you'll see it in the book, an approximation for the fraction of energy released in radiative losses for electrons of energy E. And we measure that, okay, for this equation, that energy is measured in MeVs. You have to be careful about that. And that approximation is given by the Z, which is the atomic number of the material, times the energy of those electrons traveling in that material divided by 1400. Now, if you have a mixture, if you have, for example, a particle traveling in water, so water is a mixture of hydrogen and oxygen. Basically it's a molecule of 2 hydrogens and 1 oxygen. So you can estimate an effective Z for the mixture using this equation. So F is basically the fraction of the weight of that molecule that corresponds to the atom 1, 2. Let's say we'll have an example in a moment, but you can calculate the fraction of the mass of hydrogen to the total mass of water, and the fraction of the mass of oxygen to the total mass of the molecule of water, and can divide. So let's look at that. I just wanted to understand this. So let's start with an approximation in just tungsten. So let's see. This is an example. So let's calculate. If a beam of 100 keV electrons is directed towards a tungsten target, and the tungsten target Z for tungsten is 74, what is the fraction of the total energy irradiated as Bremsstrahlung photons? So you take your calculators, think about these. Should give 30 more seconds for people to enter answers. Okay, I'm gonna stop it. So I'm gonna share the results. Most people got it right. The correct answer is B. If you answer A or C, I think, well, just keep in mind this equation that we showed you, as I said, that energy has to be input in MeV. So instead of inputting 100 in here, you're supposed to input 0.1 MeVs. And that'll give you 5.3 times 10 to the negative 3. That's basically 0.5% of the energy of those particles traveling in tungsten actually end up being Bremsstrahlung photons. But let's look now at what I was saying. Let's look now not just one element. What if we have those electrons traveling in water, which is now H2O? So think about that for a moment. Try to see if you can use this formula. I'm gonna show you how we do it in a moment, but I want you guys to think if it's understandable. And this is the fraction of the weight, say, of hydrogen, and then the fraction of the weight of oxygen and the Z of oxygen and hydrogen. So anyway, let's finish the poll and I'll go back one slide, one moment, we'll get there.
Takes a while to work this out. So
yeah. I have this slide. Okay, I think I have the numbers wrong. Try to put the closest one. Okay, let's give 20 more seconds. I see the results are very mixed. Okay, but yeah, remember the energy goes in MeV. Okay, I'm gonna stop it. Okay, most people answered B, but I think, okay, let's go to the next slide. Okay, so let's see this. So I guess the tricky part here is on how is that we deal with that effective Z. So here's what I'm showing. What is the width? So let's calculate the effective Z. So we have a molecule of water, H2O. So the total mass of that molecule is 2 hydrogens. So that will be, the mass of the hydrogen is 1. So if we have 2, it would be 2. And the total mass of that molecule of water is 16 plus those 2. So we have 2 hydrogens over 18 total nucleons that the molecule has, times the Z of hydrogen, which is 1. And of course, well, I know that I can represent this as 1/9. I'm just making it super clear that this is 2 over 18. But then we have oxygen. Oxygen is 16 over the total molecule that has a mass of 18. And then the Z number of oxygen is 8. So that's the numerator there. Similar thing for the denominator, 2 over 18. So A of 2 for hydrogen over 18 of the total molecule, Z is 1, and so on. This gives us an effective Z of 7.9.
Carlos, can I ask you a question here?
Yes.
I'm trying to really understand here, because the F, doesn't that mean the frequency of appearance? Because you're weighting F by the mass or
Yes,
by the atomic number, or is it not, shouldn't it be 2 to 1?
No, this is the fraction of the total weight of the molecule.
So it's a fraction of weight, not a fraction of the number of them.
No. So it's
Right.
like you have 2 hydrogens, but the total molecule weighs 18.
Yeah, so it's a weight, not the frequency, let's say. Yeah.
So, and I think, well, when you do that and you plug in the numbers, I think the correct answer was D. Sorry, I think I have a typo because here I didn't change the numbers from 5.3 to 5.6. But well, now that you have Z and now that you have E, let me just quickly do it. So we have 7.9 times 0.1 divided 1400. Yes, so it's 5.6 and 10 to the negative 4. So yes, the correct answer is D. Is this clear now? So that's how you can more or less estimate what's the contribution of Bremsstrahlung if now you have a mixture of elements, like a molecule of water. So as you can see, well, in this case, well, it's not a lot. In the previous case for tungsten, it was only 0.5%, at least for 100 kV. But think about this as when we deal with CT or when we deal with X-rays, there are some modalities that are not really nuclear medicine, but the way we generate that radiation is by actually shooting electron beams to a target of tungsten. And because of those Bremsstrahlung interactions, we have some radiation, and that's the radiation that we actually end up using to then obtain anatomical images of the patients. And in nuclear medicine, we're going to be very interested about water because we're going to have these effects inside the patient, and you can think that the patient has a lot of water inside. Are there any questions? Is this more or less clear so far? Okay, so here, what I'm trying to show now is a picture of different particles traveling in some area. I think this is called a cloud chamber, in which there's ionizations that happen and you're more or less able to see how particles travel. So here what you see is an alpha particle. So you see an alpha particle causes a lot of ionizations. That's why you see such a thick line, but it moves in a very, very straight line. So think about it, that alpha particle is heavy, it's hard to deflect. Here you see a proton. A proton can also be considered as a heavy particle. Proton also more or less travels in a straight line. Well, you see these little branches coming out from that initial track. Those are what we call the delta rays. Remember, we said that delta rays were electrons being knocked out of those atoms that then in itself, they can go and cause more ionizations. And here it's hard to see, but here I'm showing, this is a photo of an electron path. So the electron path is not just very straight line. You can see that it moves down, it goes up again, it moves left, it goes back to the right, it comes down. So it's more convoluted on its path. Now I think about this particle is way lighter than the alpha particles of the protons. Yeah, they get deflected as they go. But so to put it a little bit of a zoom in, this is the figure that we have in the book. A heavy proton travels in a straight line, by the electron basically moves up and down, left and right. And then you can see the emissions of delta rays. And then, so we think, okay, we saw the path. We saw, okay, either it travels in a straight line or it travels around, but we know that this particle is losing some energy as it goes. How can we quantify the rate at which these particles lose some energy? And that's something that we call the stopping power. Units of stopping power are typically given in MeV, 10 centimeters squared per gram. So let's see, what is stopping power? Stopping power, we're basically saying, what is the energy that is lost per unit length of that particle traveling in the medium? We saw that we have collisional effects, and we saw that we have radiative effects. So these are what causes ionizations and excitations, and this is what causes Bremsstrahlung. So the total stopping power is going to be the sum of the collisional stopping power plus the radiative stopping power. Now you see that I have a density here, and this is basically what we call the mass stopping power. Is basically we just normalize that stopping power, which will be just d over dx. We normalize it by the density. Yeah, because it's just basically used to normalize for density effects, and we call that the mass stopping power. Well, it's a little bit complicated to do the whole derivation of how this will look, but I'm showing you the final equation that you can then go and look for yourself if you want to look at this in more detail. I'm just going to have a quick overview of how it looks. So you have a heavy charged particle, and by heavy charged particle, remember, I'm referring to alpha particles or protons. So if you have a heavy alpha particle, we saw that Bremsstrahlung contribution is very, very low. So the stopping power for an alpha particle is basically, so for a heavy particle is just basically going to come from the collisional interactions, and it's going to look something like this. So we have a term here, which, okay, one last term has information that it has to do, it's called the shell correction term, and this is basically going to tell us, okay, how is that electron that we're knocking out bound to the atom? If it's very highly bound, then it's going to stop our particle a little bit less because it's going to be harder to get it out of there. We have particles that might travel at a very high speed. So it involves, all this comes from a derivation that involves relativity, for example. So that's why we have a beta term that it has to do with the ratio of the speed of that particle to the speed of light. Then we have many electrons there. What is the average excitation energy of those different electrons in the media? That's what this I stands for. We have to worry about the number of electrons that you have per gram. The more electrons you have there, the more interactions that particle traveling in the medium can have. And then there's this constant. This constant is called the classical electron radius, and it has that value. So if you look at this bracket, and that slowly is a very slowly increasing function of energy. It has a logarithm, it doesn't increase very fast. So what we're really concerned mostly is this term here. So for this high stopping power, then we see that, for these heavy charged particles, we see that the stopping power is just basically proportional to Z squared of the material. That's what we have here. It has to do with the density. That's why you have the density of the electrons there, and is inversely proportional to the square. So here, remember that beta term has the speed of the particle. So you have a high stopping power for highly charged particles and high density material. So high charged particle, high density material, and high stopping powers for slow particles. So if you have a slow particle, then this denominator is small, your stopping power goes high. So that's the message that I want you guys to have. It's high stopping power for highly charged particles and high density material, high stopping power for slow particles. That's for heavy charged particles. Let's now look at the betas and the or electrons. You know, it's interchangeable for this purpose. Now, in this case, we're going to have to deal. We know that for these for these light charged particles, we're going to have a big contribution of Bremsstrahlung, and we're also going to have contribution of collision. So similar, the derivation is long. If you guys want, I can give you more details. You can talk to me. But now, in this case, it looks something like this. So you have now a delta factor, and this is called the density correction. And this has to do because when there's interactions with electrons, the interactions of electrons that are further away from like the current atom are influenced by this electric field coming out from the actual atom. So there's some density correction, and the more dense you have, these effects are going to be different. Beta is what we saw already. E is the kinetic energy of, in this case, the beta or the electron. Mu0 is just representing the rest mass of that particle, and 0 c squared is just to remove c squares everywhere. So we have that there. If you look at the Bremsstrahlung emissions, and this is just an approximation, it's called the Euler equation. It's an approximation. It's only partly correct. You can add more and more terms to make it more precise. But then for the radiative part of things, it's something that looks like this. So you have a term, again, the energy of the particle, the mass. But if you look at this term here, this is those Zoom questions that we had a moment ago. Go back. Remember, ZE divided something. That's exactly what you have here. ZE divided something. And well, all this something, we're grouping it into the previous equation to get an estimation. So that's why you have, so then the total stopping power for a beta particle will be the sum of these equation on the top that involves the collisional interactions and then the radiative interactions. And yeah, so this is just for details. You don't have to worry too much. You can go as deep as you want. I just wanted to show you there's equations there modeling all these processes very, very well. It's hard to show all the derivation here, but just please know they exist. We showed you an approximation. You see why those terms are like that. You did some very quick calculations, and that's really what matters. And we can think then we have collisional losses, we have radiative losses. If you look at the contributions of each as we start, let's say, increasing the electron energy of that electron traveling in a medium, we see that collisional losses are the ones that are coming down here. They decrease with the increasing energy of those electrons, or those beta particles. They start going down. And then collisional losses, they decrease with increasing atomic number. So we have water. When we go to a heavier element that is lead, those collisional losses go down. And then it more or less reverses. As the energy goes up, we see the contribution of radiative effects start to go up. And the heavier the element, the contribution of radiative processes, again, goes higher. Okay, so then if these particles are stopping as they go, then that can leads us to define something that we call the range. We want to see on average, more or less, how far, or on average, or in maximum, how far is that particular particle gonna be able to travel in that medium. So for example, we ask questions like, how far will a beta particle from the lutetium-177 decay will travel in soft tissue? And then we can go and look, okay, the stopping power, similar to what I just showed here. We can have the stopping power that looks like this. That's what I'm showing more or less here. We have a radiative effect. We have a collision effect in red. Black shows the total. So we know the stopping power. We know that that stopping power is energy lost per length. So we can then kind of go and look for the length. So we can go to the mean range. So think about this as multiplying this dx on the left side and then dividing the stopping power on the right side and integrating on both sides. You get, if you want to look for the mean range, let's look at the mean distance that a particle will travel. Then you would integrate from 0 to the mean range, to the mean energy of the beta particles coming out from the decay of lutetium. And when you do that, that gives you more or less around 0.5 millimeters. We want to really look at the maximum range. And then similar, so now that we're going to integrate to the maximum energy that we know a beta particle from lutetium can have, and this is going to give you around 2 millimeters. So what this is saying is all that energy of that beta particle coming from lutetium, we know that all that energy is going to be deposited within a 2 millimeter radius from that nucleus of where the decay happened. So that's 2 millimeters. Our man on the previous lecture, when he was talking about radiopharmaceuticals, he also showed you, let's say, he also talked about yttrium-90. Yttrium-90 is also an isotope that has beta decay. It emits beta particles, but those particles have a higher energy. So in that case, I think he was showing, if I recall correctly, those particles can have a range of up to 1.2 centimeters. So it's higher than lutetium. And why is this important for us? So we know that we can use beta particles to treat disease. So for example, if we're treating a very, very small tumor, then we would try to target it with beta particles that don't travel too far, because particles like the beta particles of lutetium might be able to cover the full size of that small tumor. But if now we have a bigger tumor, then maybe it would be better to use yttrium-90, because we know that yttrium-90 will cover more of the length of that bigger tumor. If we treat the small tumor with yttrium-90, for example, then a lot of these betas are just gonna go to healthy organs, and we don't want that. So these are the kind of things that we also look at. We definitely need to keep in mind what is the range that these particles can travel inside the patient. There's another definition that's important to keep in mind. It's something that we call linear energy transfer. Okay, so what is linear energy transfer? Is again, it also refers to energies lost by a particle per unit length. So if you look at this, it's dE over dx, so energy per unit length. So if you look at that, you'll think, well, it looks exactly the same as stopping power. And here I'm not normalizing it by the density, but other than that, it looks the same. So what's the difference? Well, the difference is that LET, linear energy transfer, this focuses more on the energy that is deposited just in the vicinity of that traveling particle. So, and this is a very important metric that is used in radiation biology. We want to see what's the energy that's deposited where the particle is moving. We don't care if that energy is going to be deposited far away. We just look at the vicinity. So for example, if you have Bremsstrahlung photons coming out from that particle tract, well, we know that these photons are going to go far away, and then maybe they'll end up causing some ionizations further away, that then those ionizations are going to be depositing some energy. But that energy was deposited very far from the track of this initial particle. So those that energy of those Bremsstrahlung photons are not going to be accounted for in the LET. However, if you look at stopping power, that Bremsstrahlung contribution is going to be accounted for. So the energy that is deposited outside of that threshold region is not counted in the LET, but it is in the stopping power. So I hope that's a bit clear. Think about this at home. If you have questions, talk to us, and we will clarify it. But again, stopping power basically includes all the energy deposited. Linear energy transfer is we want to look very localized in that vicinity of where the particle is traveling. How much is the energy deposited? Okay, and let's finalize interactions of charged particles with talking about positron annihilation. Look, now this is particularly for positrons. This does not apply for beta minus or electrons. But assume we have a nucleus and that nucleus decays emitting positrons, beta plus particles. They're going to travel in the medium and they're going to be able to interact with electrons. When a positron and an electron interact, we have an annihilation event. And that means they annihilate each other, and what we end up with is with two photons. And there's energy conservation and momentum conservation and charge conservation in this process. So at the beginning, you have total charge is zero because you have a positive charge and a negative charge, and you end up with two photons and they have no charge, so that's conserved. To conserve the energy, well, these interactions for now, they will mostly occur at rest, so there's no kinetic energy, but then we know that the rest mass of a beta particle and an electron is 511 keV. So if we want to conserve the energy, it means that those two photons that are coming out of that annihilation are going to have 511 keV each. And because there needs to be conservation of momentum, if you think that that this annihilation is happening at rest, there's basically no momentum. So if your initial case is no momentum, then your final case has to also have no momentum. And to have no momentum, the only way of that happening is those two photons are emitted in opposite directions to each other. So they'll have the same energy, but one is going up and the other one is going down. This is going to be very important when we talk about PET, positron emission tomography. This is the basics of that. So keep it in mind. We're going to get back to these a lot. And this is just a little summary of what we've talked about charged particles. When we talk about alpha protons and heavy charged particles in general, they interact with matter primarily through Coulomb effects. This is electromagnetic forces. They are deflected very little and follow almost a straight path. Electrons from the atom can be knocked out, and that creates ionization. If those knocked out electrons can create other ionizations, well, we call those delta rays. Bremsstrahlung productions for heavy particles is small because Bremsstrahlung is inversely proportional to the mass, and these heavy particles these charged particles are very heavy, so Bremsstrahlung is low. And remember that the stopping power is basically proportional to z squared and is inversely proportional to the square of the velocity. Now for beta particles, we now have to take a lot of consideration for the two effects, both collisional and radiative. In the mega electron volt range, radiative effects are the ones that dominate. And that happens when the beta particle penetrates the electron cloud of an atom and interacts with the nucleus. This deceleration is what causes what we talked about, Bremsstrahlung photons. And again, when beta particles interact with other electrons on the atom, it can also cause ionizations and excitations. Oh yeah, so one more type of interactions of charged particles in a medium is what is called as Cherenkov radiation. So this photo on the right is looking at a nuclear reactor. These nuclear reactors emit this bluish light. But why is this blue light coming out? And well, the reason for that is that you can have particles moving at a higher speed than the speed of light in that medium. So again, nothing can move faster than the speed of light in vacuum, but things can move faster than the speed of light in some medium. And that's given by this refractive index of the material. I think this is the Snell's law, which you can have the speed of light in the medium is given by the speed of light in vacuum over that refractive index of the material. So n is always greater than 1. So this is always going to be smaller than the speed of light in vacuum. And when there's that situation, there's electromagnetic being released, which is what we call Cherenkov. And in nuclear reactors, it has like a blue type of light. Questions so far? That completes charged particles.
If I may just comment on the previous slide, again, it may sound very strange, this thing that a particle can move faster than the speed of light in a material, But that's totally analogous to the sonic boom that you would hear when an aircraft, for example, moves faster than the speed of sound. And then so it's quite analogous to that. And again, when something moves faster than the speed of light in a material in a similar sense, you get sort of a radiation coming up. And there's a lot of fascination with this process, a lot of emerging research in this area right now.
Yeah, so to add on to that, you would think, okay, well, this would probably see it only on nuclear reactors, but actually, in terms of nuclear medicine, something that has been happening is patients get injected with some radiopharmaceutical that emits, for example, beta particles. But when the physicians go and do surgery, they don't really know where the radiation is. They don't really know where to cut, for example. So one of the things that people have been looking at is they kind of turn off, or they have like this surgery room very dark, and there's some Cherenkov radiation coming from those sites inside the patient, and then that helps the physician determine, oh, I know the lesion is here, I'm seeing some light coming out of there, this is where we should cut. So that's, yeah, it has applications in nuclear medicine.